Okay, in this example, we're asked to determine whether or not a flow field is possible based on continuity. So we're told that it's predicted that a flow field has a velocity components u equal to v times x cubed plus xy squared, v equals capital V times y cubed plus yx squared, and w equals 0, where v is constant, is some constant. Is such a flow field possible for an incompressible flow? And so you can imagine that this is a situation where you're a consulting engineer and a company's done an analysis and fit a flow field to something that's going to happen in their machine or in some setting they have, and they say, okay, can you model this for us? And the first thing you would want to do is to make sure that the flow is even possible. Okay, so what we want to do is use our differential form of the continuity equation in this case. So we just write it out. So du over dx plus dv over dy plus dw over dz equals 0. The first thing we can do here is we're told that w is 0, so this is going to be 0, so that's just going to fall out. So we're left with du dx plus dv dy equals 0. Okay, so the next step is just to differentiate. So we have d over dx of v times x cubed plus xy squared plus d over dy of v times y cubed plus xy squared equals 0. Okay, so then what we want to do is just take those derivatives, and those are pretty straightforward. So we get v times 3x squared plus y squared plus v times 3y squared plus x squared equals 0. Okay, so simply looking at this equation, you can tell something. And what that is that the only place in this in a space that this is going to be true is the origin, because you have these are squared terms. So if you're not away from the origin, those are always going to be positive values. So there's no negative way to cancel those out. So what happens is that the only location where continuity is satisfied is at x equal to 0, comma y equal to 0. So this flow field is not possible because it does not satisfy the conservation of mass. And now to show you what that looks like, something like this. This is a diverging flow field. So you start at the center, you have 0 flow because all the terms go to 0 in the equation. And as you move away from the center line, the velocity, the magnitude of the velocity vectors gets bigger and bigger. And so you have a diverging flow field. Now, in this particular case, because the vertical velocity is 0, we don't have any way to satisfy the conservation of mass. However, this is a possible flow field if we make it three-dimensional, right? So if we did have flow coming into and out of the board, to offset that increase in velocity as you go away, then it would satisfy continuity. But in this case, it doesn't, and this is an impossible flow field.